Yeah, let us get started with some properties into wavelets, and these properties will essentially help us for wavelet decomposition, forward decomposition using wavelet discrete wavelet transforms. Okay. So, we start with this theorem. So, let Wj be the space of all functions such that sigma k belonging to set of integers a k psi 2 power j t minus k, the function is described by this form, and a k's are basically real numbers. So, we need to show that Wj is the orthogonal complement of Vj in Vj plus 1, and then Vj plus 1 is basically written as Vj direct sum with Wj. So, I will go with a proof sketch for one of the parts, and for the other part I will leave this as an exercise, and we can discuss the solution to the exercise. So, for the part 1, we need to show that every function in the Wj space is orthogonal to every function in the Vj space. So, let us start with some typical function in the Wj space, and let that function be f Wj, which is summation k belonging to some set of integers a k psi 2 power j t minus k. This is basically a linear combination of the shift orthonormal wavelets in this scale, right, in the jth scale. Now, let some function f Vj belong to Vj space, right. Then what we need is we need to show that f Wj and f Vj, their inner product is 0 in the L2 space, right. I mean, this their inner product is basically 0. Now, from the scaling property, so if f Vj belongs to Vj, then basically let me just denote this in simple form as some f and some g here. So, f of Vj of t, if this belongs to Vj, then if I just call this simple function as say g, like f Vj is g, then I would say g of 2 power minus j times t belongs to V0. I will call g is basically synonymous to my Vj. Just I am getting rid of this Vj so that it does not confuse us much. I could call them g and f, but I just put the subscripts Vj and Wj to indicate what spaces it belongs to. Okay. So, by the scaling property this belongs to V0. Now, consider this integral minus infinity to plus infinity sigma k belongs to z a k psi of t minus k. Now, we will just translate everything in the scale for j equal to 1, right. So, now this times g of 2 power minus j times t, let us consider this inner product, and this is 0 because psi is orthogonal to V0, right. It is orthogonal to the functions in V0. Now, this implies I want to simplify this further. So, what I would do is I would define a variable t dash is 2 power minus j times t. So, just focus on this I do a change of variable here. So, when I say t dash is 2 power minus j t, when I let this change of variable, dt dash is 2 power minus j times dt, right. Now, I can rewrite this integral slightly differently. This is going to be 2 power j times integral minus infinity to plus infinity summa k belonging to z a k psi 2 power j t dash minus k times g of t dash dt dash. This is basically 0. dt is 2 power j times dt dash. So, therefore, this 2 power j is pulled outside here. Okay. Now, what we do is, so this would imply integral minus infinity to plus infinity. I can pull the 2 power j outside. So, let me call this function as possibly f of t dash, right. I call this as f of t dash just for simplified notation. This is f of t dash times g of t dash dt dash, and this is 0. So, this implies any g belonging to Vj is orthogonal to some f belonging to the space Wj. Okay, this is a straightforward result. There is nothing out there. Basically, we use the definition of the inner product, figure out what functions reside in what space, and then we just expand using the basis in that space and then prove the property. So, this is pretty straightforward. Now, for the second part, I will give you the idea, and I will leave this deliberately as a homework. Now, when j equals 0, we showed that any function in V1 orthogonal to V0 must be a linear combination of basically these shift orthonormal wavelets. You saw the example, and from that example basically you have to formalize this result and then proceed in a general way for j not equal to 0 and fill in the missing gaps. Okay. So, now with this we will have we will establish another lemma, and probably that lemma might be useful for you in this proof. Let me sketch that statement. Let F1 be summation over k ak phi of 2t minus k, and this belongs to V1, right. This is some function in V1. This function F1 is orthogonal to V0, that is to each of the shift orthonormal scaling functions if and only if this property holds. A1 is minus A naught, A3 equals minus A2, so on. So, let us see the proof of this lemma. Now, phi of t minus L, this is basically the scaling function in V0, which is time translated. This can be written using the scales in the V1 space as phi of 2t minus L plus phi of 2t minus L minus 1. Now, let us consider the inner product of summation k belonging to Z ak phi of 2t minus k with phi of t minus L. So, what we need is if f1 is orthogonal to V0, then this property must hold. So, that means we should consider the inner product, set that to 0 and then examine what we can. Now, let us look at the inner product of f1 with phi of t minus L. So, this can be written as sigma k belonging to Z, because now you can exchange the summation. I mean, we have studied this property of inner products. So, you can exchange the summation and then you can take the inner product of phi of 2t minus k with phi of 2t minus L, because I expand, like let us say if I say this is equation 1, say this is equation 2, I say use 1 in 2, right. Then I could do this way, plus the inner product of phi of 2t minus L minus 1 with phi of 2t minus k. I mean, these terms really look ugly, but it is very easy to simplify them. Now, just ponder at this inner product here. Both of these are box-Carr functions, L2 space, but with different time translates, and they exist when k and L coincide. So, basically this can be written as delta k minus L. When k equals L, it exists, otherwise it vanishes. Similarly, you look at this inner product. This is basically existing when k coincides with L plus 1, right, and this can be written as delta k minus L minus 1. Now, this is a summation on the outside. You have some AKs and then you have deltas, and they will exist only when k equals L here. So, therefore, you will end up with a trivial statement that AL plus 1 is 0. This implies AL plus 1 equals 0. So, plug in L equals 0, 1, 2 dot dot dot, right, and I think I should write this to be equated to 0, because this is where we start with the condition that f1 is orthogonal to each of phi of t minus k. Okay, now there is at least one existential result here. You can figure out what is one nature of this function f1 if it has to be orthogonal to V0. Okay. So, hopefully you will use this property in proving the result which I gave you as a homework for part B.